Hello everyone. So all right, we are going to discuss pumping lemma here. I am going to tell you what is pumping lemma, what is the use of pumping lemma, why we use this, and we'll take an important example and let you know that how to solve any problem with the help of pumping lemma. So let's start. Basically, in terms of regular languages, there is a great use of pumping lemma to prove any non-regular language as a non-regular. Focus. To prove any non-regular language as a non-regular, we use pumping lemma. The simple definition is every regular language can be accepted by a finite automata. You all know it, that every regular language can be accepted by a finite automata, a recognizing device with a finite set of states and no auxiliary memory. It means that without any extra memory, some finite states of automata is there and which is going to accept all your regular languages. The finiteness of the set is used by the pumping lemma in proving that language is not regular. It means that the finiteness nature of the pumping lemma, we are going to use this and will prove that any language is not regular. It is important to note that pumping lemma is not used to proving whether a language is regular. It is rather used to proving if the language is not regular. It is not used to prove any language is regular or not. It is only used to prove whether a language is non-regular. Just to prove non-regular as a non-regular, we use it. We don't use it in reverse, right? You can't use this lemma to prove any language is a regular. No, you only use it in order to prove that it is non-regular, right? So one concept, this should be clear to you. Now, what lemma exactly says, the pumping lemma states that for a regular language L, there exists a constant n such that every string W in L such that the length of W is greater than or equals to n. We can break W into three substrings. W equals to XYZ. We are breaking the string W into three substrings X, Y, and Z, such that Y is not null. This Y is not null, and X and Y should be less than or equals to n. For all I greater than or equals to 0, the string X, Y to the power I, and Z is also in L. The lemma states that for a regular language, every string can be broken into three parts, X, Y, and Z, such that if we repeat this Y I times between X and Z, then the resulting string is also present in L. If the resulting string is not present in L, it means that it is non-regular. Okay. Don't worry, we'll take an example and we'll let you know that how to solve it. But before that, just focus on the applications of the pumping lemma. The pumping lemma is extremely useful in proving that certain sets are non-regular. The general methodology followed during its applications is select a string Z in the language L, break the string Z into X, Y, and Z in accordance with the above conditions imposed by the pumping lemma. And now check if there is a contradiction for the pumping lemma or not for any value of I. If there is a contradiction, it means that it is non-regular. Okay. So basically, pumping lemma is contradiction-based algorithm to prove any non-regular language is a non-regular. Now let's take an example. Let's say there is a language L equals to a to the power n and b to the power n, where let's say n is greater than or equals to 1. We have to prove that this is non-regular, So how to implement this pumping lemma? First, just go contradict. Just go contradict. If we have to prove it is a non-regular, then step 1, assume L is a regular. Assume L is regular language. Okay. Now, if L is regular language, it means that there is a certain finite set of states on which this language will be accepted, isn't it? Because if it is a regular language, means regular expression is possible. If regular expression is possible, it means that finite sets are possible, of finite state sets are possible in which this language will be accepted. Then we can say that it is regular. So if it is regular, it means that finite automata is possible, and then that finite automata may consist finite sets. Let's say k states it is containing. Let's say k states, the finite automata contains k states, because if it is a regular language, then finite automata must have, and if it is have, then let's say it is having k states. Now let's say a to the power k and b to the power k is there, which should be greater than or equals to k. Step 2. How I am saying this? Because if there is a finite states are there, then it must satisfy that on completely revolving around that states, on completely revolving around the finite automata, it must be accepted there. If it is accepted, it means that regular, but if it is not accepted, it is non-regular. However, we cannot prove that any language is regular or not on the basis of that, but only we can prove that it is non-regular. So I can write it, I can break the string, this W string, into 3 strings, into 3 substrings X, Y, and Z. Let me break it into the 3 substrings. I can break it like, let's say A, and in between A, if in between this A is there, then it is nothing but it's K minus 1 and it's B to the power K. Because K is a certain number of set. Our problem was to prove a to the power n and b to the power n, where n is greater than equals to 1 as a non-regular, correct? So let's say for particular k states we are taken the problem, and if it is a non-regular, if it is a regular, then it should be followed, it should be accepted with the finite set of states. And I can break this problem into these 3 substrings, because if I am taking it X, Y, and Z, Y is A, if Y is A, then X would be A K minus 1 to balance this, isn't it? And this B to the power K is Z. Okay. Now X into Y to the power I and Z, it should be followed for every value of I should be greater than equals to 0. Why? Because it follows the principle of Pigeonhole, that if let's say value of I is 1, if the value of I is 1, it should be 1. In that case, a to the power k minus 1 into a and b to the power k, it's nothing but it's a to the power k and b to the power k, which is a part of our language. But what if the value of I is 2? If the value of I is 2, in that case, it would become a to the power k minus 1, a square and b to the power k, because y to the power I is there. I have to break this string in this format, X into y to the power I and Z. If I put I to the value as a 2, in this case, what is the resultant string? The resultant string is a to the power k plus 1 and b to the power k. But this string is not part of my language, isn't it? This string not belongs to my language. Thus I can say that it is not following pumping lemma. It is not following pumping lemma. Because if it is following pumping lemma, then on repetition of it on I many times, it must be accepted somewhere. Because if it is a finite length string, or it may be some kind of infinite length of a string. And if it is a regular, it means that somewhere cycle may be exist, or somewhere loop may be exist. And with the help of the loop or with the help of cycle, it would repeat and will be accepted. But here you can simply see that if I can increase the value of I as a 2 or 3 or 4, that is more than 1, in that case my resultant string will become like this, which is not a part of my language, because my language is a to the power n, b to the power n should be greater than equals to 1. It means that a and b should be equal, but here a and b are not equal, because pumping lemma says that I have to take a string length just one greater than the number of states. If my finite automata is having n states, then the pumping length should be n plus 1. So that I can say that if any string of n plus 1 length is accepted by this finite automata, it must have at least one cycle or loop. Thereafter, we can say now that it would be accepted by finite automata, because if I am taking n plus 1 length string and my finite automata is having only n states, in that case, how this string is going to be accepted on the final state? I must have any cycle or any loop. They're only possible now. This is the concept of pigeonhole principle. This is the concept of pigeonhole principle, isn't it? Using that, we can simply say that if we are going to increase the value of I, but the resultant string is not part of our string, hence this string is not possible. It means that it is not following pumping lemma. So if it is not following the pumping lemma, it means that it contradicts our assumption. It contradicts our assumption. What was our assumption? That L is a regular language. But it contradicts because it fails to provide that it's having a pumping lemma. That's why we can say that this is a non-regular language. This is a non-regular language because it failed to aspire all the properties of pumping lemma. Okay, so this is all about pumping lemma. I hope the concept is very much clear to you. Further, if you are having any kind of doubt or confusion, you can ask me. Thank you so much. Have a very nice day. Jai Hind, Jai Bharat.